The addition and subtraction property proofs. Um, this could be probably one of the harder proof lessons, just so you know. And these proofs don't show up on every Common Core exam, but they do sometimes show up. They have in the last couple years. One here, or just maybe I'd say out of 5 proofs on an exam that you'll get over a 5 year span, one of them might have addition subtraction. So what we're going to get this year, I'm not too sure, but it's really not terrible. It just takes a little bit of thought as you kind of go through the problem um, in order to break it up and kind of see where you need to be. So I've already put the givens in the proof for you, but let's just see what we have. We have DC is congruent to AF, and I know these triangles look like they're overlapping, but they're kind of not in a way that they don't cross over each other. They're just kind of leaned up against each other. But you can see there's this little space, and that's actually what they're giving you. They're giving you DC is congruent to AF, just these two little parts here. So that's kind of interesting because it's not a full length of a segment. Our goal is to get triangle EDF congruent to triangle BAC right here. And because we are trying to get these two triangles congruent with just these little parts here, we're not going to be able to use this little part and this little part to give us a full side. So what we're going to need to do is add on this little piece right here, which is reflexive, something that those two triangles share. They both have CF in common. So if we added DC to CF, we would get that full length, and if we added CF to AF, that would get us the full length right here, and eventually we'd have DF congruent to AC. So you're trying to build up to a full segment. So that's kind of where we're at here. Let's just get the other things in. We've got perpendicular. FD is perpendicular to ED, so you have a right angle here and a right angle down here. I'm trying to squeeze them in along with the other markings. And then you have ED congruent to BA. So what we're going to end up with is a side, angle, and eventually side of these two triangles. I was going to get rid of that last S so it's a little easier to see. But all right, so we're going to write this up, kind of see where we go with it. And we have the givens in, and I'll get right to the new part here. So let's talk about how to get eventually DF congruent to AC. What we first need to do is put this reflexive piece in, and a lot of students forget this. They forget to write in that CF is congruent to CF. So don't forget that part, because when you're trying to make two different longer pieces congruent, it's important that you know that the reflexive piece is the same, and it allows you to make a full congruent segment. I know that sounds confusing, but I can explain it more in person if need be. So that's reflexive. And then what we have in step 3 is that, and here's how we'll write this one up, that these two pieces, DC and AF, we're going to make them part of an equation. I know, usually we don't see equations in proof, but we're going to say DC plus CF, which is the reflexive piece, and we're going to use is equal to, because we're adding parts together, and then AF plus CF. And since they both have the CF part in common, and we know that the reflexive pieces are congruent and DC is congruent to AF, what we're going to do within the same step here, and I usually just, I'll draw in something that you can draw, and it's hard to draw it in here. I'm just going to put that we know DC plus CF is really DF. And that now is congruent to AF plus CF, and AF plus CF is really AC, which is the other piece we need. And usually what I do is I will draw this in like this. I'll just kind of put this is that, and this is that. But you don't have to. I'm just kind of showing you where these two things are coming from. Okay? All right. And then the reason for this is our new thing here. This is called the addition property. The addition property allows us to add like pieces that we already know are congruent to each other, and then it gives you a longer piece that's congruent. So the fourth step here is that we need to say angle D and angle A are right angles. So I'll get into that. That came from perpendicular. So I get my little angle symbol here. And that is, let me just copy it, because I'm going to need it. So we're going to say angle A and angle D are right angles. And this came from definition of perpendicular. I'll just type it out, but you could use the symbol. And step 5, we already had DE is congruent, or ED is congruent to BA, so we just have to say these angles right here are congruent. We're going to say angle A is congruent to, give my congruent symbol, angle D. This is all right angles are congruent. Okay. And so we have everything we need. We already have this piece here. We have the right angles are congruent, and then we've got the longer piece we use with addition. So I could say this step right here and the reason is side angle side. So I'm going to say side angle side is congruent to side angle side. All right, so that's the addition version of these proofs. Now let's take a look, I'm sorry, I didn't mean to scroll so fast, but let's take a look at the subtraction version of this. It's really just the opposite. Instead of having the two small pieces added onto a little bit longer piece, we're going to take the whole thing, subtract away pieces that we want, and then we're going to end up with smaller pieces that we want to get congruent. So it's kind of just the opposite version of it, and I think you'll notice that you'll kind of see a common theme here. Okay, so in this proof here, our goal is to get triangle ACD, which is the triangle right here. Put a little dot there. We're trying to get this triangle congruent to triangle BCE, and in order to do that, we're going to have to use something called subtraction. I'll show you what that looks like. So we already have AC is congruent to BC. We have AE congruent to BD. So you can see they overlap. It's too long. We got this whole thing right here congruent to this whole thing right here. And what we want to do is sort of cut this piece right out, leaving us with this piece congruent to that piece. Okay, so let me just get rid of some of that there. And so our goal in the end is to get this piece congruent to this piece. We're out of givens here, but we remember that if we have an isosceles triangle, which now the big triangle is isosceles based on AC congruent to BC, you get this angle congruent to this angle, and this is side, angle, and side. So we're going to write this one up just like we did the last one, and you'll see how this works. So let's go here. After our givens, we want to say, well, I'll do the hard part first. So we're going to kind of work here. All right, I want to first say that DE is congruent to itself. I still need that reflexive piece in there. So DE congruent to DE, this is reflexive. And then here's the subtraction part. I want to say eventually that AD is congruent to BE. So what I'm going to do is start by saying AE minus DE is equal to BD minus DE. BD minus DE. And that'll get you BE is congruent to AD. So it's just like the last one. We're going to write a little equation. I'm going to say AE minus DE is equal to BD minus DE. And underneath it, I'm going to say that these two things, when you subtract them, AE minus DE, that's really AD. So I get AD is congruent to, and BD minus DE leaves you with BE. And this is called subtraction property. Okay? And this is all in the same step. And I mean, you can sometimes you can put it in parentheses underneath it, but I always just kind of, like I said, I'll just draw this in. I'll just say, okay, so this is that, and this is that, and it's the subtraction property. So just more of like a small little notation way to do it. Okay, I'm going to say angle A is congruent to angle B. Put a little angle symbol here again. Angle, copy that because I need it. Angle A is congruent to angle B. And this is because of the isosceles triangle theorem. Oops, 4. Okay, and then I believe we have everything, right? CA right here, AC is congruent to BC. We've got the angles at the bottom, we just said, and we've got the piece AD congruent to BE. And step 5 is this here. And the reason is side angle sides congruent to side angle side. Okay. And so that's it. That's how you would write this proof up. There's a couple more here. Now, I do want you to notice something. In proof 3, they're asking you to get these angles congruent. And what I want to tell you is what you would do is get the triangles congruent, and then after that step, so you'd do everything you would normally do to get triangle CAD congruent to triangle CBD. Then after that, this step right here you can say, and this is this thing called CPCTC. I believe in the isosceles triangle video it does pop up, and I'm not sure if I actually covered one like that. But it's something I can go over with you in person. It's really quick. It's one extra step past the proof. So you literally would get the triangles congruent by whatever reason, and I could quickly label this and figure out what it is. So CD bisects AB, so you got this piece here. CE is congruent to CF, and EA is congruent to this piece. So we'd want to do addition, add this piece to that piece, and it'll equal this piece plus this piece. That gives you CA congruent to CB, and then you could use reflexive. Once you get the triangles congruent by side, 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 you could then say this thing is congruent, and the reason is called CPCTC, and all that means is since the triangles are congruent, all of their matching pieces are now congruent. So that's just something to know, and I could always show that to you in person, but it's really not a difficult thing. This is one step past the actual proof. All right, so give these a try, and this was addition and subtraction, one of the more, I guess, complex concepts in the proof unit. All right, good luck.